are going to start a new topic. It is called greedy approach. Like that's one of my favorites because it's not very hard to detect greedy problems, and usually they are not the most challenging ones, you know, like some other problem types, like they can be challenging, it might require a lot of effort, but most of the time greedy problems, they are easy to detect, at the same time easy to implement. So there is not much trick going on when it comes to greedy approach. But now we should first understand what it is. So, greedy approach is an algorithmic paradigm that builds up a solution step by step, always choosing the next step that offers the highest benefit. So what does that mean? Like, what is the meaning of the word greedy? Nobody knows? Or everybody knows that it's so trivial that nobody wants to tell? Somebody, Khalid, what is greedy?
Someone who doesn't want to give up the thing they're holding.
Who doesn't want to give up what they hold? Okay, I would say it's close. In our context, greedy means more of like a person who always wants to get the most. You know, it doesn't think about the long term much. Like it is greedy, you know, like wants to own everything, wants to have everything, kind of. And when it comes to solving problems with greedy approach, what we are doing is, at any given step, we look our options. And then we try to choose the option that brings the most benefit, most immediate benefit to us. And then we go with that option. So obviously you can take that kind of approach for pretty much any kind of problems, but you're not going to get to the optimal result in the end. So therefore, in order to apply greedy approach and get the optimal result, we need some, like the problem needs to satisfy some conditions. And if these conditions are not satisfied, then using greedy approach will not yield the perfect solution. So, what are these conditions? Like basically, we are going to get to these conditions after this slide, but now let's think about this sentence. Choosing local optimal steps must yield to global optimal in the end. Meaning, like, think about this greedy guy. That person, he is always making decisions in the most immediate, for the most immediate benefit. In order for this guy to be super successful, all of his local optimal decisions should yield him to the global optimal in the end. And good news, there are two conditions that we can check for any given problem to see whether that problem can be optimally solved by greedy approach or not. So these properties are greedy choice property and optimal substructure property. So now let's take a look what these properties are. So we start with greedy choice property. It says from a local optimum, global optimum is always reachable without taking a step back. Meaning, if you solve one of the sub-problems in an optimal way, if the global optimal solution is depending on that sub-problem solution, then you don't have to take any step back. You can use that sub-problem solutions as it is to reach to the global optimal solution. So that's the first property. I think it's going to be more clear with the examples, but I think up to this point it should make sense. Like, obviously, if the local optimum is local optimum solution cannot be used to reach the global optimum solution in the end, then we need to take a step back. It means if we always get the most immediate benefit at any given step, we cannot reach to the global optimum. So the second property is called optimal substructure property. And it says optimal solution can be determined from the optimal solutions of the subproblems. There is no guarantee that each subproblem solutions are going to be useful, but in order to decide the optimal solution for a given problem, considering some subproblems optimal solutions would be enough. So now let's take a look at some examples. I think it's going to be more clear after that. So the first problem we are going to think of is called fractional knapsack problem. So we are given goods with different weights and values. And we are trying to collect as much value as possible for the given capacity. And goods can be captured in fractions. What does that mean? Like knapsack is the name of the bag that the thieves carried in the old days. I don't know if there are still some old school thieves with such bags anymore. But in fractional knapsack problem, basically the thief is trying to fill up their bag, their knapsack, and they can get each item fractionally. So that is the part that is not realistic, like it doesn't represent the real world situation immediately or exactly. So basically, normally, like if a thief comes to this lab and wants to steal some stuff from here, they cannot divide the screen into 2 or 3 parts, right? It's not possible. So they cannot take things in fraction. But in this problem, imagine it's not about stealing goods from a lab, but we are stealing goods from a warehouse. So they have different types of plants over there, and like they are all in very small form. So we can get as much as we want. So in that case, let's think whether greedy approach can yield us to the optimal solution or not. So we had 2 conditions, right? The first condition is greedy choice property. So now let's check whether this fractional knapsack problem is satisfying greedy choice property or not. So the property says from a local optimum, global optimum is reachable without taking a step back. What does that mean? Let's say this is our knapsack. And we want to fill it up to the capacity, right? This is the capacity. In order to get here, can we use optimal solution for one of the sub-problems to get to the global optimal? So, if we fill this part up in an optimal way, can this be used for finding the solution for C? Yes. And in order to see why this is, let's do proof by contradiction. Let's imagine there was a better way of filling this part. Sorry, let's say there is a way of filling this part, like the C optimally up to this point, without taking the optimal solution from this sub-problem. This would mean that we should be able to fill this part up with more value than that is captured here. Like if V2 that yields to C is greater than V1, then V1 cannot be optimal. Because if V2 is greater than V1, it means for this C1 sub-problem, we actually had a better solution. So in that case, V1 wouldn't be the optimal solution for C1. Are you guys able to follow this? Okay. So now let's look at the second property. Let's do the check for optimal substructure property, which says optimal solution can be determined from the optimal solutions of subproblems. So, for this problem again, let's say we have the optimal solution for C1, and we also have the optimal solution for C minus C1. Would putting these two together give us the optimal solution? Or is it guaranteed that this is going to be the case? Since we can take things in fraction, it is guaranteed, right? I mean, if it was like 0-1 knapsack problem, then we don't know whether the optimal solution would come from C1 or C2 or C3. Because like maybe we have one item that gets like this much of a space in the knapsack, so taking this is valuable, that's why we might want to put it in the first place, and the solution could have come from another subproblem. But since we can take things in fraction, we don't have to consider this case. Like if we want to reach to the optimal problem of C, we can basically merge the optimal solution for C1 plus the optimal solution after taking out these elements, because obviously like each good has some limit. If everything was unlimited, then the optimal solution would always come from getting the good that gives us the best value over space ratio, right? And since it's not the case, like after taking out the used part from this, basically we are going to solve the remaining subproblem here with the remaining goods, and then we are going to fill this part up optimally as well, and in the end we will get the optimal solution for C. So any questions about the problem or the way we approach so far? So can somebody tell how the solution code would look like?
First we fill it up with the best value for space until that runs out, then we go to the next one until our knapsack fills up.
Yes. Like obviously here the limitation comes from not all the goods are available in the infinite amount, right? So they are going to finish at some point. So we will start from the most valuable item and we are going to put as much as possible from that. And if it finishes before then we reach to our capacity, we are going to go to the next best item. And we define goodness of an item by its value over its weight or the space it takes from our knapsack. So is this approach clear to everybody? And as you see, like it's such a simple algorithm, right? And it gives us the optimal solution under given circumstances. So the second problem we are going to cover is called activity selection problem. And in this problem, we are given activities with start and end times. And we are supposed to choose the most number of activities that do not intersect with each other. What does that mean? So now, let's imagine we have some activities given on this timeline. So this is 1 in the morning, and let's say this is midnight. This becomes 6, right? Okay. So we have one activity here, starts here and then ends here. We have another activity, starts here, ends here. Another activity like this. Another activity like this. Another activity here. Activity here. Activity here, let's say. Yes. And obviously, choosing different activities at the beginning will yield to different results in the end, right? Like given that we cannot be in 2 different places at the same time yet, we should choose where to be at any given time. So let's say if we choose this activity, like this is taking a lot of time, right? If we choose to involve in this activity, then we are going to be missing this one, this one, this one, and this one. But these 2 are still feasible. And we can choose one of them to have together with this one. Is everybody clear with the problem? Okay, so now let's add some numbers. We said this is 1. Let's say this is 4. This is 2. This is 3. This is 5. This is 6, 7, 8, 9, 10, 11, 12, 1, 2. This piece here. All right. So now, let's take a look at the criteria. So the first property is greedy choice property. And it says, from a local optimum, global optimum is reachable without taking a step back. Let's say we are planning our day, and up to 7, we have the perfect program. Is it possible to have a solution which is optimal from 1 a.m. to 6 p.m., but it has a better solution for 1 a.m. to 7 a.m.? I mean, if it had a better solution for this part, then the solution for this sub-problem wouldn't have been optimal, right? So if this sub-problem solution is optimal, then a solution for 1 a.m. to 6 p.m. should either contain this optimal sub-problem solution up to 7, or should have an activity that actually has 7 inside. Because if we are not using this optimal solution, it means there is an activity that is selected for the optimal solution for 6 p.m., which is intersecting with 7 a.m. Otherwise, this sub-problem solution would have been used for the big solution. So is this part clear? Alright, so now let's take a look at the second property, which is optimal substructure property. Optimal solution can be determined from the optimal solutions of... Okay, what happened? Can you please reconnect the cable? Yes. Okay. So, yes, the second property that we are checking is called optimal substructure property. An optimal substructure property says optimal solution can be determined from the optimal solutions of subproblems. So now let's take a look. We want to decide on the optimal solution for 1 a.m. to 6 p.m. If we look at the solutions for 1 a.m. to 2 p.m., 1 a.m. to 1 p.m., 1 a.m. to 11 a.m., 1 a.m. to 10 a.m., 1 a.m. to 9 a.m., and all these, can we construct the optimal solution for 1 p.m. to 6 p.m.? Like first off, if we know the optimal solution from 1 a.m. to 2 p.m., then it's going to be equal to 1 a.m. to 6 p.m., right? Because there is no activities after 2. And another one, if we know the optimal solution from 1 a.m. to 1 a.m., then I can basically consider whether I should get the last activity in this one or not, to see if I should add this last job or not. So basically, if I take a look at all these sub-problem solutions, I can figure out the optimal solution from 1 a.m. to 6 p.m. So solving the sub-problems in an optimal way would be enough to construct the optimal solution for the larger problem. Any questions about this one? So, can anyone have a guess on how would the solution look like for activity selection problem? Yes?
Actually, it's a question. Can this qualify as a greedy approach? Because we're checking whether we have to remove the last one to add a new one in. Aren't we taking a step back?
Actually, like the last thing I said, it wasn't about taking a step back, because here the sub-problem up to 1 would still be valid. It's just like that one cannot be merged with this one. But the sub-problem up to 11 can directly be merged with this one. So it's like the reason we were taking, like I said, we were taking step back was actually considering another optimal sub-problem solution, which is up to 11, since the last activity is intersecting with this one. But normally, yes, we don't take step back. So it's better to say that here, when we are looking to construct the optimal solution, we can either get this sub-problem solution, since this is intersecting with, this cannot be added on top of this, or we can get the sub-solution for this, and then add this activity to construct the optimal solution up to 2. Okay. All right. So any suggestions on how to solve this activity selection problem? All right. At this point, let's take a break, and then for 5 minutes try to solve the problem. Okay. Everybody, let's work on it, and we will continue after 5 minutes.
Spending the time with as many as possible activities, or having most of the time
Involving in as many activities as possible. Any guesses? Yes.
At each step, add the shortest activity with the shortest time span. That does not intersect with any of the activities that we have in our list. Take the shortest, the activity with the shortest time frame. We add it to our schedule. And then we go to the next activity that is the smallest.
Uh-huh.
That does not intersect with the previous, the added activity.
Okay. How about this?
We have the smallest, which is the last.
You start with this one, and then you take it, and then you're going to return answer one. So it's the counter example. Nice try. Don't be afraid of trying, guys. This is how we get to the working solution, right? You have one idea, and then you give it a try, and then you try to refuse it. If you can refuse it with a counter example like this, and then you continue thinking to find another idea. But that's a very good start. So is everybody clear with the problem? Like to formalize, we can say like we are given n represents the number of activities. And in the following n line, in each of the following n lines, we have one activity. Start and end time. And return the number of maximum number of activities return the most number of non-intersecting. Yes. So for this problem, let's say this is 1, 2, 3, 4, 5, 6, 7, 8. We have 8 activities. And the first one is from 1 to 4. The second one is from 3 to 6. The third one is from 5 to 7. Then we have 2 to 9. Then we have 8, 11, 10, 11. So this is 8, 11. And this is 10, 10, 1. 10, let's make it 13. And 13, and then we have 12, 14. Which one did I forget? No, we have 7 actually. Yes. And the expected answer for this one would be, like we can pick this one, and this one, I think. So it's going to be 4. Yes.
We can start from 1 and until we find the end point of the activity. We can go one by one, 1, 2, 3. At 4 we find the end of the first activity. So we add this. And
Okay.
this is our actually local optimum. So we start from 4 until we find the end of activity which which its start has to be after 4.
Uh-huh.
And when we found this is another local optimum. So we start from there. Can I show it on table?
Yes, I think I get it. So basically you start from the beginning and then you look for the activity that ends the first.
Mm.
And then you get that activity for sure. So basically it means till 4 I have two options. I can either be involved in no activities at all, or I can be involved in the first activity. So which case do we like more? Like which case is more helpful for our purpose? Which one? Being involved in that activity, right? So then we say, okay, up to 4, I can only accomplish one activity because there is only one activity. And there is no point in not being involved in this activity because any other activity I choose is gonna occupy me until a later time. So that's why it makes a lot of sense to get this activity for sure. And after that, after I choose this activity, what I do is, again, I ask the same question, but this time my start point is 4. So I'm asking, okay, when is the next activity that ends earliest and starts after this point? Because if it starts before 4, I cannot be involved in those activities, right? Basically, by adding this tick, I am also adding these crosses as well. But note that this didn't have to be the activity that starts the earliest. This is the one that finishes the earliest. If this was 3-4 instead of 1-4, I would still pick this one. Because I care about the end time. I don't care about the start time much. Is this clear? Okay, after this, we see that the next activity that finishes earliest and starts after 4 is 5-7. Is there a point not taking this activity? Because after this, that's the earliest that is finishing, right? Any other activity that I'm going to be involved is going to keep me busy for till a later time. So that's why it makes more sense to be involved in this than the others. So that's why I get this one. And then I also cancel all the activities that starts before 7, but they were already cancelled. So at this point, what I'm going to do is, I'm going to search for the next activity that starts after 7 or at 7 and that finishes the earliest, which is in this case this guy. This finishes at 11, this finishes at 13, and this finishes at 14. So I decided to get this one. And then what am I going to do? All the activities that starts before 11 are going to be cancelled now because I cannot be in 2 places at the same time or more places. And finally, I do the same thing after 11, and there is only one activity left, and I get this one. And this is how I reach to the optimal solution for the given problem. And as you see, like we solved the sub-problems optimal way. And that's how we constructed our solution for a larger window in the end. Is this clear? So now let's think more. How we can implement this? Because if we start with your first suggestion, we start from 1 and check if there is any activity finishes here, and then go to the 2 and then check if any activity finishes there. If the activity lengths are from 1 to 1 billion, then this is not going to be feasible solution, right? Or let's say if they are up to 10 billion, it's not going to be feasible for sure.
We can sort the activities based on their end time.
Yes.
Tamam.
Once we do that, once we sort all the activities by their endpoint, as in this case, what is going to happen? We will start and there is no blockage at the beginning, right? So I'm going to say yes to this activity. And then what am I going to do? I'm going to continue iterating on this list until I find an activity that starts after 4. Is this starting after 4? So I say no. Is this starting after 4? Yes. So my new end time is 7. So now I check if the next activity starts after 7 or not. So I cannot take this one. Is this one starting after 7? Yes. So I can take this one. And How about this guy? Now my new endpoint is 11. And 10 is before 11, so I cannot take this one. But this one, yes. So what is my time complexity now?
Why?
O?
Why?
The sorting.
Oh.
Depending on your
Oh,
sorting
okay,
algorithm,
okay.
right?
And okay.
I mean, if you use an n log n sort, then it's going to be n log n. If you use a linear time sorting, then it's going to be O n. So it
But
depends on your implementation.
If we know the times, I think we can use counting sort. So
It depends on the range of the times. Like if the range is from 0 to 10 billion, for example,
Yeah.
then you cannot use counting sort. But still you can use radix sort. So you can still make it better than n log n. The arithmetic time complexity. So any questions about how we solve the activity selection problem? Is the solution clear to everybody? And now let's take a look at, again, now that we have the solution, let's try to understand why greedy choice property and optimal substructure property are both satisfied. So, greedy choice property says, from a local optimum, global optimum is reachable without taking a step back. So now let's consider here, at time 4, we said the optimal solution is getting the first activity, 1, 4. Now, this way we finish one activity before 4, right? This is the optimal solution for this. Is this solution used for the optimal solution for till the end? Right? We didn't change it, we didn't modify it, we used it exactly as it is. So greedy choice property, like being greedy at the beginning, oh, I want to accomplish as many tasks as possible until 4, actually worked out well. That's why greedy choice property is satisfied. And the second one is optimal substructure property, saying optimal solution can be determined from the optimal solutions of subproblems. So it is important to understand this very clearly. It doesn't say that optimal solution should come from any given subproblem optimal solution. What does that mean? So I'm trying to give you a counter example right now. Yes. So I have these activities. Okay? So now let's take a look at the optimal solution at this point. Let's say this is 1, this is 2, this is 3, this is 3, this is 4, this is 6, this is 7, this is 10. So now let's take a look at the optimal solutions at 7. The optimal solutions at 7, like 1 is 1, 2, 3, 4. The other optimal solution is 1, 2, 3, 7. Right? So, if I'm looking for optimal solution up to 7, if somebody says 1, 2, 3, 7 is an optimal solution, is this correct? That is correct. But if I want to construct a perfect solution till 10, can I get to this solution by using this subproblem's optimal solution? No. So it doesn't say that any kind of subproblem's optimal solution is going to yield to the perfect solution here. Okay? So you might have to use another subproblem solution, or you might have to change the definition of your optimal solution. Because if you define your optimal solution in a way that, in the case of equivalency, like having the same number of activities, choose the one that finishes earlier. Then, with this definition, the subproblem 7's solution is going to be 1, 2, 3, 4. And now you can use this subproblem's optimal solution to construct the perfect solution for the larger problem. So, are you guys clear with this? What we are saying is just one of the sub-problems solution is going to help us to construct the perfect solution, the optimal solution for the larger problem. But not all of them necessarily should yield to the perfect solution at that step. Okay? And it's because, obviously, as you see, like the ones that are intersecting with the activities that are starting before, earlier than the end point, like basically the sub-problem solution that we are looking for, and that end after. Because of these activities, this can change. So now, are we clear about greedy choice property and optimal substructure property? Alright, in that case, let's take a look on the last problem that we are going to cover today, which is called Egyptian fraction problem. So the problem is actually very easy to describe. Given any fraction, we want to represent it in the form of 1 over x1 plus 1 over x2 plus 1 over xn is equal to the given fraction. Let's say if our given fraction is 5 over 6. How can we write it in the form like this? Let's think about it. Like basically what we want is we want to use fractions for which the upper side is going to be 1 all the time, but the lower side can change. We decide on it. So if it is 5 over 6, for example, maybe we can write it as 1 over 6 plus 2 over 3. But it's not still in the form that we desire.
1 over 2 and 1 over 3?
1 over 2 plus 1 over 3. Yes. 3 plus 2? Yes. So that would be one of the solutions. Is everybody clear with the problem? Okay. Now let's think for a solution.
Isn't there a trivial solution to this problem? Like, we could just take the denominator as is, and then take 1 repeatedly until we get the denominator. Like 1 over 6 plus 1 over 6 plus 1 over 6.
Oh, you want to make repetition?
Yeah.
Oh, okay, so I should say x1 is not equal to... Otherwise, yes. Okay, now take your time. I mean, you can use pen and paper. I want solution.
Should the denominator have to be increasing order? Like for example,
I mean, it can be any order. Let's say in the end we can sort it, right?
okay. But it should not be equal to 6, right? Can it be 6?
It can be equal to 6, but they are not going to be equal to each other. So basically, this is not allowed to write it like 1 over 6 plus 1 over 6 plus 1. Oh, and it's not like there is no restriction on that. Yeah.
I didn't know the solution. Can it be greater than 6 also?
What's that?
Can it be greater than 6?
Of course.
No, I didn't.
And so on, right? So, which fractions are we allowed to use? Like we are allowed to use 1 over 2. Oops, this is dying, I think. Like we are allowed to use 1 over 2, 1 over 3, 1 over 4, 1 over 5, etc. Right? So, if the fraction that we are dealing with is greater than 1 over 2, is there a point of not taking 1 over 2 out of it? I mean, we have to represent this positivity with other fractions anyways, right? There is no escape. All the value in here has to be distributed over these guys, right? If this guy is greater than 1 over 2, is there a point in not taking 1 over 2?
No.
No. That's why what we are doing is we are basically finding the largest number that is in the desired form, largest fraction that is in the desired form that is smaller or equal to the given fraction. So in this case, we start with 1 over 2. And we get 1 over 2 out of 5 over 6. And then we have 2 over 6, which is equal to 1 over 3. And since we reach to a fraction which is already in the desired form, we stop there. So let's take another example. 7 over 8. Is this greater than 1 over 2? Yes. Therefore, we take 1 over 2 out of it. And we have 3 over 8. Is this greater than 1 over 2? No. And we cannot repeat it actually. We can skip 1 over 2 after. Is 1 over 3 greater than 3 over 8? No. No. Therefore, we take out 1 over 3. And this is actually 9 over 24. And this is 8 over 24. And then the remaining is 1 over 24. So basically, we picked 1 over 2, 1 over 3, and 1 over 24 to represent 7 over 8. So now the question is, like, I guess, like, is everybody clear with how the algorithm works? So now yes.
Can we be sure that we produce an output for every possible number? Is there a way of proving that?
Yes, like if you keep doing, like basically the algorithm continues until it reaches 1 over something, right? So it's either it's not going to reach to 1 over something, which is not the case in the simplified form, it's going to get that. Right now I don't know the mathematical proof for this, but I'm pretty sure you can prove it. And if it's not in the form of 1 over something, then you continue applying the same algorithm. You take out some of the fraction. And since basically all the, like we have all possible fractions can be written in this form, therefore it's going to reach the point where we are done. We will have 1 over something. Okay, so is everybody clear with the algorithm? How it works and why it works? Okay, so now let's try to make it faster. Because right now, let's say if the number that we are dealing with is 1 over 2 plus 1 over 3 plus 1 over 24 plus 1 over 10 billion 1. Then like we will be looking for, is this greater than this one, this one, this one, this one? Too many lookup. So to make it faster, actually, Kale made a suggestion. How about using binary search? Because we know that, like if 1 over 1 billion is greater than the remaining, then I have to go to the right. There is no point in checking things that are greater than 1 over 1 billion and say whether that number is smaller than the number I have in hand or not. So binary search can make this faster, yes. But can we do it in an O1 time? Just by looking at the remaining number, can we say which fraction is going to be the largest smaller fraction?
We could divide the numerator by the denominator and have it as a decimal. Then
Or the numerator by numerator.
the numerator by the denominator. Yeah.
Yes. So basically for this example, if we divide 8 over 7, and then are we getting the floor or ceiling?
The ceiling.
Yes. And use this as denominator. Then what is going to happen? Like what this is telling us is actually 1 over 2 is the largest fraction in the form of 1 over something that is smaller or equal to 8 over 7. Sorry, 7 over 8. So now let's try another example, like, because this is just 2, right? What if it was in the form of like 9 over 47, for example. What are we saying is, let's divide 47 by 9. And then let's get the ceiling of it, which is 6. And we basically say, okay, so in this case I should take out 1 over 6. So now we also know how to get to the point in all one time, right? To the right fraction. Like with this algorithm, we are jumping to the right fraction immediately, rather than iterating over them linearly. So now, like, is everyone clear with the solution? Okay. So now let's check for the greedy approach properties. So first we are going to check for greedy choice property. It says, from a local optimum, global optimum is reachable without taking a step back. Like in this example, when I take 1 over 2 out of 5 over 6, am I taking an optimal step or suboptimal step?
Optimal.
It's an optimal step, right? I need to represent this positivity in the form of 1 over something fractions. And we know that 1 over 2 can be written as 1 over 2, or it can be written as 1 over 4 plus 1 over 4, or it can be written as 1 over 8 times 4. Right? And which one uses the least number of terms? 1 over 2. Therefore, there is no point in not taking 1 over 2 in the form of 1 over 2. So, by solving this sub-problem after we take out 1 over 2, we have a way to get to the optimal solution for 5 over 6. And now let's check for the optimal substructure property, which says optimal solution can be determined from the optimal solutions of subproblems. So in this case, 5 over 6 optimal solution comes from 2 over 6 optimal solution. Again, we can construct the optimal solution for the larger problem by looking at the optimal solutions for its subproblems. So the problem actually satisfies both conditions. That's why by using greedy approach, we can get to the optimal solution. So if we didn't satisfy one of the criteria, you can still use greedy approach, but there is no guarantee that the solution you get is going to be optimal. And in programming competitions, like 99.99% of the time, they are not looking for a solution. They are looking for an optimal solution. So in that case, if our problem in hand doesn't satisfy the criteria, then we shouldn't use greedy approach. All right. So any questions about greedy approach, the greedy choice property or optimal substructure property for the problems that we had covered so far? In that case, we are going to finish the class with quote of the day. So this time our quote comes from Bruce Lee. And he says, do not wish for an easy life. Wish for the strength to endure a difficult one. Because if you have an easy life, then it's going to be easy, man. Anybody can live your life. So you're not going to have any extraordinary outcomes. But if your life is difficult, but at the same time you have the strength to cope up with all the challenges in that difficult life, then your life is going to be way more impactful than many other people's easier lives. Thank you very much. And we will continue with the practice session.